This work investigates the nonlinear streaming current, which fundamentally should be linear behavior. So as you can see here, this yellow one is a porous medium. So when we have a highly charged porous media on top of the microchannel surface, then we have a nonlinear streaming current. So to analyze this, we built a microfluidic device like this. So it has a tournament channel to increase the throughput. So when we push the Nepean solution into this side and fill it and dry by heat, and then we have a very thin coating on each microchannel surface. So this is the fabricated device. So when we push the electrolyte through this side, and then we can measure the streaming current. So as expected, the bare PDMS means without any porous medium, and then this linear behavior we can observe, so like in this black dot. But once we have a Nepean coating inside the microchannel, and then this straight line, it become curvy shape, like in this red and blue dot. And also the nonlinearity is strongly depending on the electrolyte concentration itself in this graph. So to analyze this, we set up this numerical domain and separate the streaming current into diffusional contribution and conduction distribution due to the 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 induced electric field inside this porous medium, because the when we have a very small nanopore, the the convection inside this nanoporous medium is also non-negligible. So applying the induced streaming current actually push back in this blue one, push back the ions so that we have a very small alternation in this streaming current. And also this one is pressure driven, which is the main contributor. So, and also the last one is electroosmotic flow against to this convective flow. So as you can this graph, the diffusion and electroosmotic flow is negligible, but as you can see here, as the pressure driven convection increase, the conduction contribution is also increased. So this behavior is the key mechanism of this work. So based on this calculation, we can have dn is the thickness of the Nepean. So it's 0 means the bare surface. It should be linear, but when we have a certain amount of the charged surface, and then it become curvy, like this red and blue one. And also the bulk concentration, it affects to the electrical double layer. So when we have a high concentration and a very thin electrical double layer, so that we have a large influence to the nonlinearity. So this one can be analyzed by scaling law. So when we have when we tune the thickness of the Nepean, concentration of electrolyte, N is the charge of the surface, and pi p is the porosity, and tau is the tortuosity. So by analyzing this black line and red line influence the largest among these other parameter. So this work can be the this work can be useful for designing the sensor, because usually the sensor should have a linear behavior. But when you do some surface treatment, then it became nonlinear. So when we tweak something, some parameter in this graph, then you still have a linear behavior.